We're given a function in this question, f of x, whose derivative is given by u divided by v. And furthermore, we're told that f dash k, so we're putting in some value in for x, is equal to 0. Now, that would mean that u k over vk is equal to 0. And the only way that this can be possible is if uk is equal to 0. Because I'm dividing two things, you can't divide by something to give something else is equal to 0. Like if this was like 5, you can't do 5 divided by any number to get 0. It must be that uk is equal to 0. So we just need to bear that in mind. Let's find f double dash x to start with. We can use the quotient rule for this, and we're going to get u dash v minus uv dash. This is one to learn, divided by v squared. And therefore, f double dash k is going to equal u dash k and vk minus uk v dash k all over vk all squared. But we've just said that uk is equal to 0. Therefore, I can just get rid of that. And you know what? I'm going to jump straight to it. Because that's gone, I can now cancel out a factor of vk. And so I'm simply going to get u dash k divided by vk as required. And this question, it then moves on to talking about this kind of graph, which I'm just going to move, in fact, over here. And it gives us an equation. Now, bear in mind, we're probably going to have to use this fact later on. It might have just been asked in isolation, but just be aware of that when you do a question like this, that it's going to be useful at some point. So in B, we're given this function, and we're told it crosses the y-axis at point A. Here we go, because it's figure 1 sketches C together with its 3 asymptotes, these lines, these dotted or dashed lines in this case, where the curve will never touch. And then we're asked to find the coordinate of point A. So that is going to be when x is equal to 0. So y will equal 3 divided by minus 1, which is simply minus 3. And A is therefore 0 minus 3. Then asked to find the equations of the asymptotes of C. So it's worth thinking about the fact that it's a fractional quantity, and we could factorize the bottom because you're interested in basically where that might equal 0. So x plus 1, x minus 1. And you can see this function will not exist when x is equal to minus 1 or x is equal to 1. That's going to be some possibilities. X equals 1, x equals minus 1. That's what will cause this jump, this discontinuity. And then we've got this other one. Now we can see that it says x gets really big, that the curve is sort of tending towards it. So that's what we need to look at. As x tends to infinity, y will tend to, you can look at this and you can think, because x gets really big, now that basically is going to disappear, and that is going to disappear. It's not going to come into it. And then as x gets really big, or x squared is going to get really big, but look, you can see that these are going to get really big kind of by the same amount, this x squared and this x squared. And what the function is going to tend towards is that 2. So as x tends to infinity, y will tend to 2. Do you know what? Maybe I should just put a little bit more working in. So it'll actually tend to 2x squared over x squared, which is equal to 2. And therefore, the other asymptote is going to be y is equal to 2. Next up, we're given that the point P lies on C, where A is greater than 0 and B is greater than 0. Okay, we'll think about that. Or no, I know it can't be here. Like A is greater than 0, so it's got to be this side, but it can't be down here because B is also greater than 0. So I can put it on, maybe I put it here. Okay, that can be point P. And then what else do we have? The point Q also lies on C with PQ parallel to the x-axis and AP equaling AQ. So if it's parallel to the x-axis, it's going to be sort of along here, and it's going to be here, which by symmetry, did it call it something? I can't remember. Q. So it's going to be Q minus AB. And we've also got this point A. And furthermore, it said that AP is equal to AQ, so this all checks out. Okay, I didn't perfectly draw it in line, but it should be. And then it says, show that the area of the triangle PAQ is given by this. So I've drawn the triangle in. What I'm interested in is finding this area. All right, well, now let's look at this. So I see that the base is simply going to be given by 2a. Now I need to look at the height. Actually, maybe I'll put it on the right. Well, I know that this is minus 3. So I can actually work out what the value of b would equal because I can substitute it in to here. So b must equal 2a squared plus 3 divided by a squared minus 1. And therefore this height is going to be that 2a squared plus 3 divided by a squared, minus 1. I'm going to have to minus 3, which is the same as adding 3. Now I'm in a good position to figure this out. Put it down here, so part 3. So the area will equal half times the base times the height, which is this thing here. And somehow it's going to simplify down to that. Let's try and do that. Well, I can cancel out that half with the 2. I'll leave the a outside for the moment. The main thing we have to do now is add these two things together. So it's going to be 2a squared plus 3. And then I can put it over common. Actually, I just put an extra step in. And then it's going to be plus 3 lots of a squared minus 1 all over a squared minus 1. Put it over a common denominator. That will be 2a squared plus 3 plus 3a squared minus 3. And it looked quite complicated, but now we can see that these cancel. So I'm going to get 5a squared, but I'm going to times that by that a to give me 5a cubed. And then I've got my a squared minus 1 there as well. Good job. In this last part, we're asked to find as A varies the minimum area of the triangle, giving our answer in the simplest form. So we can imagine moving these points, that we could move them to the left or to the right, and what's going to happen. I think it makes sense there's not going to be any maximum, because if you just kept moving them higher and higher, then you can make the triangle basically as high as you want, but always have a width of at least this distance here. So there's going to be and also the same going the other way. You can make it um, wider and wider here with keeping the height always at least this. But there's going to be a point at which we get a minimum. But actually, what's generally expected is that we still prove it's a minimum. I don't know if words to the effect of what I've just said would count. So we have the area. We're going to need to differentiate. Now, if this is u and this is v, then u dash will be 15a squared and v dash will be 2a. So we get this, which I'll now simplify. So 15a to the 4 minus 15a squared minus 10a to the 4. And this is equal to 0 for stationary points. Now, because it's equal to 0, it must be that this top part is equal to 0. And this is already bringing back memories of part A, where we had that the derivative was a fraction and it was equal to 0. So we concluded that the top was equal to 0. Now that u is basically now this u here, and this would be v. So we'll bring that back in a bit. So this will imply that 5a to the 4 minus 15a squared is equal to 0. That's essentially ua is equal to 0. I know it's a little bit confusing because I've been calling different things u, but I'm now calling it u here. And I can factorize out a 5a squared. But a is not equal to 0, so it's got to be that a squared is equal to 3. So a is going to be the square root of 3. We know it's positive because that was the definition earlier on. Now, as I said before, if like this must create a minimum surely, and you can see the minimum would be when it's minus root 3, like it's the same triangle in that case. And surely we could just justify it through that explanation that I gave, but just to be on the safe side, let's um let's look at the second derivative. So we know that f double dash a, actually I just need to, basically I want to now bring back in this part A. I'm not actually going to differentiate again this thing here. I don't need to, because using part A, we know that we have the top of the fraction is equal to 0. That's how we solve to get a equal to root 3. And so it follows that f double dash of a in our case is equal to u dash a divided by VA. That's a little shortcut that we can make. Using part A, since UA is equal to 0, and F double dash A is equal to U dash A divided by VA. And if we differentiate, we're going to get 20A to the 3 minus 30A divided by A squared minus 1 squared. And when A is equal to root 3, this equals, to be fair, we could have just done F double dash root 3, couldn't I? But I didn't. It's going to equal 20 times root 3. I just wish I'd factorized that A out. I'm making my life a little bit harder than I needed to. Because I want to be squaring it really. So before I substitute in, I'm gonna, should I factorize it out? I just factorize out the A. So when I substitute root 3 in, that'll be much easier to deal with. Remember, we're not really interested in what it's equal to, just whether it's greater than, or that it's greater than 0 to give a minimum. So it's going to be 20 times root 3 all squared, which is going to be 20 times 3, which is 60. Then I'm minusing 30. And I'm dividing by a positive. I'm actually going to be dividing by 4. And this will be greater than 0. Hence, A equals root 3 gives a minimum. And the minimum area, we just need to substitute root 3 back in, where was it, into here. So it's going to be 5 times 3 root 3 divided by 3 minus 1, which gives 15 root 3 over 2. Quite a nice question, I think. Really satisfying result.